So we're going to move on to talking about particular types of functions. And so today we'll look at linear functions and models. And we're going to start each section the same way. We're going to start by just simply solving some equations and inequalities. And in this case, linear equations and inequalities. So let's take a look at the first example, because this should be review for most people. And so we want to solve this first equation here, x over 2 equals 4 plus x minus 35 divided by 5. So this is kind of a tough linear equation to solve because you have these fractions. And so the idea is just to clear these denominators. And the way we're going to clear denominators, and we're just going to simply try to find a number that we can multiply by that clears the denominator. So we have to multiply by a number that involves a 2 and a 5. And so, of course, that's the number 10. So we'll multiply everything by the number 10. And so over here, we'll have x over 2, so I'll do this in 2 steps. I usually skip this step, but x over 2 times 10, and then equal to, we'll do 4 times 10, and then plus, we have an x minus 35 over 5, all times 10. And so what's going to happen is the denominator is actually going to go away, so a 10 divided by 2 is a 5, so we're going to get a 5x here, equal to a 40, plus, and then a 10 divided by 5 is a 2, so you're going to get a 2 times x minus 35. And so you'll notice what has happened is that we've cleared the denominators. There are no longer any denominators here. And then the next step will be to multiply through by this 2 to unlock the x, and then we can get all the x stuff to one side. So what we're going to have is a 5x on the left equal to, then we have 40 plus, and then we have a 2x, and then a minus, a 2 times 35, which is minus 70. And so then we combine like terms, so we have a 5x on the left, and then a 40 minus a 70 is actually a minus 30, so we have 2x minus 30. We're going to subtract 2x from both sides to get all the x's to one side. And we're going to wind up with having 3x on the left equal to a negative 30 on the right. And then, of course, we'll divide out now by the number 3. Right, since you're multiplying by 3 to move it over, we simply do the inverse, or the opposite if you like, and we divide. So we divide both sides by 3, and we get x equal to negative 10. And what's really nice about solving equations is you can go back and actually check your work by plugging in a 10 over here for x. So if you plug 10 here, 10 over 2 is 5. If you plug 10 into here, this number right here should also be the number 5 when you crunch it. Let's go to the next problem, which is solving an inequality now. And it's a linear inequality. What makes this linear is you just have x. You don't have an x squared or x cubed or anything like that. So this one, again, it's a tougher linear inequality. And the way that we are going to solve it is we're going to clear the denominators. Now, on this one, we can actually multiply it by a number that's a little bit smaller than 2 times 3 times 4. So if you multiply all these numbers together, it will also clear it, but that's actually a 24, I think. Yeah, 24. But if you multiply this by the number 12, it will also clear the denominators, because the idea is all you really need is to clear the 4 and the 3, because a 4 here will clear the 2 also. So if we want to make this simple on ourselves, we simply can multiply by the number 12. And so everything here, everything, all 4 things get multiplied by the number 12. And so when we do this, if you take x over 3 and multiply it by 12, what are we going to get? We're going to get 4x, because 3 divided by 12 is 4, minus, if you multiply 3 halves by 12, the 2 and 12 are going to give you a 6, right? So this is going to be a 3 times 6, which is 18. Right? Notice that 12 divided by 2 is 6, basically, and 6 times 3 is 18. It'll be less than or equal to, when you multiply this by the 12, it's going to divide the 12 by 4 and give you 3, so you have 3 x's. Right, x on top times 3, plus multiply the 1 by 12, and you get 12. So there I just cleared denominators all in one step. And now the idea is get all the x stuff to one side and everything else to the other. So maybe I'll do this in 2 steps. I'll add 18 to both sides. So on the left-hand side, I have a 4x. On the right-hand side, I have less than or equal to 3x plus 30. And then I'm going to move over to 3x, so minus 3x from both sides. So solving an inequality basically is just like solving an equality. The only difference is if you multiply or divide by a negative number, you have to remember to flip that inequality sign. But right now we're doing just fine. And so we'll subtract 3x from both sides, and we'll get an x on the left, and less than or equal to the number 30. And so my answer, we can write it on a number line, and then we can put it in interval notation. Here's 30, and we're less than or equal to. So we have this closed bracket, all the things, this bad squiggly line, all the things to the left of 30, basically. And so you can write that as minus infinity to 30, and then square bracket because you want to include 30, because that's when it's actually equal to. And so that's how we solve linear equalities and inequalities. Let's take a look at the question here. What is a linear function? And so what you want to realize is that you do linear things all the time. So for example, if I go and buy gas, and let's make gas a nice number. Suppose it's $2 a gallon. So if you go buy gas, you're going to use a linear concept, because if you buy 10 gallons, you're going to multiply that by 2, and you're going to pay $20. What we say here is that the $2 per gallon, at least for that day, is a constant rate of change. You also do this when you buy pretty much anything in a store. So suppose you're going to buy a cantaloupe, and a cantaloupe is $1. Right, if you buy 5 cantaloupes, you take 5 times 1, you're going to pay $5 because it's $1 per cantaloupe. Right? And so that's the idea. It's a constant rate of change. So whenever you have a constant rate of change, you're going to be working with a linear function. And again, you do it all the time. Getting paid by the hour, like minimum wage. Suppose minimum wage was $8 an hour. Let's suppose it was $8 an hour. All right, so that's a constant rate of change. So if you want to figure out how much you're going to make over a 10-hour period, you multiply it by 10 hours, and it tells you you're going to get $80 basically. Right, minus some money because you have to pay taxes on it or whatever. But whenever you have a constant rate of change, you're going to deal with a linear function. So what we're going to do next is we're going to look at a linear function through the different types of ways to represent them. We'll look at some of the table, a basic graph, and then we'll do some formulas. And then we'll finally conclude this section with sort of some modeling stuff, how to use linear functions to model things. So let's take a look at using tables. So here's example 2. And I give you guys 2 tables here. We have table A and table B. And the first question is, which table is linear? So let's take a look at the tables and see if you can't figure out this sort of pattern in each table. So the inputs here are changing by 1 on both sides here, so you're just adding 1. But what's happening over here is what we kind of want to figure out. So what's happening? 0, 3, 6, 9. So if you look at these, you'll say to yourself, well, each time it looks like I'm adding 3, right, to get to the next one. Whereas over here, you have 4, 8, 8, 16, and 16, 32. So if you think about it, you're not adding 4, because if you were adding 4, when you add 4 here, you get to 12. So that's not right. So another way to get to 4 to 8 is you multiply by 2. And that looks good. So if you multiply by 2, it goes to 8. If you multiply 8 by 2, it goes to 16. If you multiply 16 by 2, it goes to 32. And so these are 2 tables. They follow 2 different patterns, and you want to ask yourself which is the simplest, simpler pattern. And hopefully you're like, well, adding is simpler than multiplying. So this is probably the linear table. And it is. And so down here, we'd probably write table A. So A is a linear table because you're adding the same number each time. Whereas over here, you're multiplying. This is actually what's called an exponential table or exponential data. And we'll talk about this later in the semester. So exponential, let's say data or table, whatever you want. And so let's try to figure out just from this table A. We're just going to work with this table A now, from now on. We're going to figure out what is the slope, or the average rate of change of this table. Right, so what's the average rate of change? Well, it's just a change in the output divided by the change in the input. And so you can actually take numbers, do 3 minus 0, divided by -1 minus a -2. Or you can just look at it and say, look, it's changing by 3 each time. So the average rate of change is 3. Right, so the idea is if you go up by 1 input value, you go up by 3 output values. All right, so now let's talk about the x-intercept and the y-intercept. Now this can be a little bit tricky to try to keep them straight, but remember the x-intercept here, when I think of the x-intercept, what you want to think about is the wording of it and say, okay, well you have an x-axis and you have a y-axis, and what the x-intercept is, it's where you cross the x-axis. That's why it's called the x-intercept. Now you do not know how far over you went, but I know I went up 0. So basically the output is 0. So for the x-intercept, I look in my table, I try to find the output of 0, and there it is right there. So the x-intercept is at the point -2, 0. Whereas the y-intercept doesn't occur along the x-axis, it's going to occur along the y, so somewhere around here. It could be positive or negative. So I don't know how high up it is or how far down it is, but I know that the input is 0. And so that's why the other one right here is the y-intercept. And so my y-intercept is 0, 6. And to figure out what the graph looks like, you can simply graph these 2 points and connect the dots. So to graph a line, you only need 2 points. So you have the point -2, 0, which is right here. And then you have the point 0, 6. So you go over 0, up 6. And then we're just going to take those 2 points and we're going to connect them with a line the best we can. It doesn't have to be perfect, but we'll connect them with this little line right here. And that's our graph. And then finally, what would the formula be? So now remember, formulas are found from patterns. They model forms, and so you can kind of guess at the formula just by kind of thinking about how the table works. So if you look at the table, the idea is you start at 6, and to get to the next number, you simply add 3. To get to the next number, if you have a 2 here, I bet this number you would add 3 again. Right, so the idea is that the output y is equal to, you start at this value 6. So when you plug in 0, you start at 6. So let's say you start at 6, and then you're just going to add 3 each time. So for each input value that you go up by 1, you go up by 3 over here. So you're going to add 3x. Right? So what this says is you start at 3, and you're going to add 3 each time. Now some people might like to write this as y equals 3x plus 6, which is really the same thing. It doesn't matter, but sometimes we like to write this because of this what we call slope-intercept form, which we'll talk about in a little bit. Y equals mx plus b. So you can actually read off the y-intercept is at that 6, and then the slope is actually 3, which is that average rate of change of this function. All right, so that's sort of using a table to try to work with linear functions. Let's take a look at some of the graphing stuff. And before we do that, let's talk a little bit about understanding slope, because slope is actually intuitively an intuitive idea that we all kind of understand. So let's take a look at a few examples here. So here you have some slope. I have some lines here. So some no slope, a little bit of slope, and then let's do a lot of slope. And then let's do it on the opposite side over here, a little bit of slope going down, and then let's do a lot of slope going down. And so the letter we usually use for slope is m, which is sort of interesting because nobody really knows why we use m for slope anymore. There is some people that believe it comes from a French word that has connection to the word of slope, but nobody really knows, which is kind of interesting. But here in this problem, let's just talk a little bit. What do you think no slope would be? So if I had no slope, I would probably assign what number, basically? I would probably assign the number 0, and that's what no slope is. So no slope means 0. A little bit of slope going up, this is actually, let's say we can make it positive. Let's make it +1. Right, so positive actually means you're going up. And a lot of slope going up might be like, let's say +10. Right, there's a lot of slope going up. And then going down, of course, instead of positive, you just make it negative, which intuitively makes sense. If your slope is negative, you're not going up, you're going down. And over here, instead of +10, you can make it -10. That means a lot of slope going down. And you can even then make sense of these types of numbers, because really, the slope, there's all kinds of ways to memorize it. But we can say it's the rise over the run, if you want, of the line. That's a common way. You can even be a little bit more precise and say it's the change in the output, delta y, over the change in the input, so delta x. The change in the output values over the change in the input values. And so when then you look at things like, what does it mean to have 0 slope? That means if you go over a little bit, if you go over 1 unit, right, how many units do you go up? You go up none, which makes sense with 0 slope. So you go up 0. Versus if you have slope 1, what does that mean? That means if you go over 1 unit, you get to go up 1 unit. So you go up 1 unit. That's what it means to have slope 1. Versus slope 10, so that means if you go over 1 unit, you don't just go up 1 unit, you go up 10 units, which gives us this idea of a very big slope. And how about -1? This is even a little bit more neat, I think, because it's like, hey, if you go over 1, if the slope is -1, then you don't go up, you go down 1, which again, intuitively makes sense. You go down 1. That's why it's -1. You go over 1, you go down 1. What does slope -10 mean? Well, it means if you go over 1, then you don't go up 10, you go down 10. Right? So you go down 10 units. Right? So negative 10. Right? So intuitively, slope makes sense to all of us. I mean, we all think about I'm hiking up a hill and it's got a lot of slope, right? Hiking up a really big hill or something like that. So it's really steep. And so if you're going up this way, it's positive, whereas if you're going down the other way, it's going to be negative. So let's take a look at a couple examples here. So the first example, we want to find the slope of this line, and then we're going to do it 2 ways. We can do it intuitively by finding a couple points here. So here's a point here, and here's a point here. So if I want to find the slope intuitively, all I need is really 2 points, and I can say m is equal to, and I just look for that rise and run. So here's a run right here, and then going up, there's a rise. And so I can do that. And now the rise is 2, and of course the run is just 1. And so what's my slope? Well, it's the rise over the run, the change in the output of the change in the input. So it's 2 over 1. It's positive because you're going up, so the slope is 2. I could also, though, use a formula. So remember the slope, if you want, if you have 2 points, you could write it down as this. You could say m is equal to, and it could be kind of fancy if you like, so delta y over delta x. And you could write things, a formula down, say y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And this is just a fancy formula for the slope. I know this formula. I don't think it's bad to memorize, but remember, formulas are not the point. Really, the intuition is what you want to develop, and the formulas will follow from your intuition. But we can use formulas. So you have a point here, which is 0, -2. And you have a point here, which is just 1, 0. And so what we can do, if you want, is we can use this formula and say m is equal to, and it's just a change in the outputs divided by a change in the input. So let's take this output value of 0, and then subtract off this output value of -1, or -2, sorry, and then divide by this input value of 1 minus this input value over here of 0. And so what do we get? We get a 2 on top, because minus and negative is a positive, and a 1 on the bottom, and so that's equal to the number 2. Which is exactly the same answer I got over here, but these are 2 different ways sort of to solve this problem. One, I'm using my intuition, which is always important to be able to do, and then 2, I'm using a formula. Right? Probably the most important is to be able to develop the intuition, because from the intuition I can usually develop the formula, although a lot of times in math people will try to memorize the formulas and see if the intuition follows, and often doesn't. So think about how you do this intuitively, and then typically you can develop formulas once you master the ideas with your intuition. X-intercepts and y-intercepts, I already found these actually. They were the nice points. So for the x-intercept, that's right here. And so that would be 1, 0. And then the y-intercept, of course, is along the y-axis, which is right there. And that's 0, -2. And then to find the formula for this line, I can kind of use my intuition to try to understand, what the formula would be. And in a minute, I'll give you a ways to find the formula using formulas, y equals mx plus b. But intuitively, the idea is my output is equal to, well, at 0, you start at -2. So I'm going to start at -2. Remember, the idea of a linear function is you have a constant rate of change. So basically, you're adding the same number each time. You start at some value, like in this case -2, and then you're going to add some number each time, and the number you're adding is this slope, this rate of change, which is just 2. So it's -2 plus 2, and each time we multiply by x. So the formula is just -2 plus 2x. Or you could rewrite this, if you like, as y equals 2x minus 2. And so there's a formula for this line. You can even check it by plugging in another point. If you plug in 1 here, you see you get out 0. If you check 2 points and it works, you know it's right, because there's only one line that goes through 2 points. All right, so let's talk about the last thing here. The last thing I want to talk about is I want to talk about the formulas. And so there's 2 formulas for a line. I'm going to start with what's called the slope-intercept form. So the slope-intercept form is mostly developed from our intuition. The idea is y equals, you start at this value b, and you add the same number each time, so m times x. And that's what it really means to be linear. You start at some number, and you add m each time. And these letters have meaning, of course. M is called the slope, and the b is the y-intercept. Right, so that's the y-intercept. Now, where the slope-intercept form is important is when we're trying to figure things out, like what the slope of a line might be. It's good for our intuition, really. So let's take a look at an example of this. So here, I want to work with this linear formula, with linear formulas, and I want to use the formula to answer the following questions. All right, so I have this 2x plus 6y equals 30, and I want to find the slope of this line. So what we can do is, we know this formula. You memorize this formula, y equals mx plus b. It sort of fits with our intuition. You start at number b and you add m each time. And what we can do, though, is we can take this equation, right, this formula here basically, and solve for y. And if we solve this for y, I can read off the slope and even the y-intercept. So let's solve this for y. So the way we're going to do this is we're going to subtract 2x from both sides. And so let's do it. Let's just do it down here. So I'm going to copy this down right here. So 2x plus 6y is equal to 30. And we'll subtract our 2x from both sides, because I'm trying to solve for y, so I can get it in the right form. Y equals mx plus b. And so I'm going to get 6y on the left, and then a negative 2x plus 30 on the right. And then I'm going to divide both sides by the number 6. And so when you're solving equations, you just use the same operation of both sides, and the equation will remain balanced. And so y is equal to, now when you divide everything by 6, I'm going to divide the negative 2 by 6, and also the 30. So this is going to look like this. So it's going to be negative 2/6x plus 30 over 6, which is where students often make a mistake. So you remember, when you divide with addition, you have to give the 6 here to each of them, not just to the 30, but also to the 2. Now, if it was multiplication, you could just give it to the 30. That's why we're typically getting confused. And then, of course, this reduces to 1/3, so it's negative 1/3 x, and that's a plus, and 30 divided by 6 is 5. So there's the formula, and then, of course, y equals mx plus b form, and so you can just read off the slope. Here's the slope m, which is exactly the same position here, which is negative 1/3. So m is equal to negative 1/3. And then the y-intercept is the b, which is just the positive 5. So you can write y equals 5 if you like, or I'll just write the point 0, 5. That's the y-intercept. And then finally, we want to graph it. So to graph this, you can just graph this one point, 0, 5. So here's the point, 0, 5. And I can use my intuition, my understanding of slope, to actually graph it. So remember, these numbers have meaning. So this 3 has a meaning. And then this negative 1, I'll put the negative on top. This negative 1 has a meaning when you talk about slope. So on the bottom, remember, it's the rise over the run. So 3 is the run. So what I'm going to do is I'm going to go over 3. So go over 3. 1, 2, 3. And then it's a negative 1. So instead of going up, I'm going to go down 1. So I'm going to go down 1. And this is another point right here on my graph. And so then I can just connect those dots. It's the best I can. And that's the equation of my line. So that's just using my intuition now to graph it. Now I can also use my skills sort of with just working with formulas. So another way to graph this would simply to be to make a table, basically, right? So an XY table, you know if you plug in 0, it's clear you get out 5, so there's 1 point. And then another point you can plug in is just plug in, I probably wouldn't plug in 1, because if you plug in 1, then you have negative 1/3 plus 5. So you pick a number that's nice, like plug in 3. And 3 is a nice number because when you plug in 3, do you see how the 3's will cancel? So when I plug in 3 here, I'm going to get negative 1/3 times a 3, and then plus a 5. And of course, that's a negative 1 because the 3's cancel, and I add 5, and I get a 4. And if you think about it, 3 comma 4 is exactly that point I found right here. So that's the point 3 comma 4. And you can simply connect the dots that way. So you got lots of options. You can use your intuition, your sort of understanding of slope, where 3 is the run and negative 1 is the rise, or the fall in this case, because it's negative. Or you could just do a table and plot a couple points and connect the dots. The next problem I want to look at involves the slope point form. So let's talk a little bit about the second type of equation, right? So you have the slope intercept form, and it's called the slope intercept because you have the slope and the intercept. And then we have what's called the slope point form. The slope point form involves the slope m, and then this x sub 1, y sub 1 is a point. I want to talk a little bit about where this formula comes from. You know, the slope intercept form sort of comes from our basic intuition. The idea is you start with a number b and you add m each time, so that's how you develop that formula, really. But this formula comes from more of the geometry. So the idea, you can think about it if you want to know where this formula is coming from, is you just have an x and y axis, and then you have a line. I'm just going to draw some generic line there. So this is some line. And the idea is I have a point on this line, which we're going to call x sub 1, y sub 1. So that's some point on this line. And I have some, and I'm going to take some other point on this line, and I'm going to call it xy. And I know there's a relationship between these points. Because they fall on this line, I know that they have basically the same slope. So if you calculate the slope using these 2 points, you're always going to get out the same number. So what I know is that if I write down m, I can write it down in terms of the rise over the run. So basically, you can do y minus y sub 1, which is the rise between these 2 points. And then I can divide it by, the run of these 2 points, which would be x minus x sub 1. And I know this always holds for any xy on this line, because that's what a line really is. It has constant rate of change, and the rate of change is the slope. Now notice what happens if you clear denominators on here. If we clear denominators, if we multiply both sides by x minus x sub 1, what's going to happen is you're going to get m times x minus x sub 1 on the left, and the x minus x sub 1s on the right are going to cancel. And so you're going to get y minus y sub 1, which is basically this formula, right? Written the other way, right? So, you know, y, same thing, y minus y sub 1 is equal to m times x minus x sub 1. And we call this the slope point form because, again, you're given the slope and a point. Whereas we call the one above it the slope intercept form because you're given usually the slope and the intercept. So slope intercept form is great when you're trying to work with things and use your intuition. Now slope point form is good when you're trying to do things in a more sort of mechanical way and you may lack some of the intuition. So let's take an example of this using the slope point form. So we want to find the equation of a line through the points negative 1, negative 6, and 1, 2. So first let's just plot the points because I think sometimes this is helpful. So here's the point right down here of negative 1, negative 6. And then the point 1 comma 2 is right here. So you go over 1, you go up 2. So here's the point 1 comma 2. So this is a step that students often skip. And you can skip this step. It's not a huge deal. But what's nice about this step is that when you do compute the slope, you see it should be probably a bigger number. Like it shouldn't be like a fraction, like a half or a fourth, because it's kind of steep. But you also see the slope is positive because the line's going up. So in order to find the equation of a line, I want to use this formula, y sub minus y sub 1, which again, you're going to memorize, but it comes from the idea of slope, the rise over the run. Changing the output of it, changing the input to constant, basically. So I want to use this formula. So for this formula, I got to find a few things. What things do I need to find? I need to find the slope, and I need a point, x sub 1, y sub 1. Now what's nice is you have lots of points. So I'm going to choose, you have 2 points, basically. I'm going to choose these 2 points. I'm going to choose this point, 1 comma 2. That's a nice point. It's an easy point to work with because both the numbers are positive. You could also have chosen the point below it, right down here, -1, -6, but it's a little harder to work with because you have negatives. So I have a point, but I don't have the slope, so I need to go find the slope. So let's find the slope on this thing. And so remember how you find slope. Slope m, it's equal to the rise over the run, or if you want, you just write delta y over delta x, just to remind yourself, is a change in the output, a change in the input, and you can just go find it. It's pretty easy to find. You just take the difference in the outputs, that's the change, so 2 minus a -6. So on the top, I'll put a 2 minus a -6. And then on the bottom, I have the change of the inputs. Now remember, if you start with 2 here on top, you start with the 1 on the bottom. So it's 1 minus a -1. So on the bottom, you have 1 minus a -1. And then you just crunch the numbers, and the answer falls out. So on the top part, you have 2 plus 6. On the bottom, you have 1 plus 1, because a minus is positive on both parts. And then you get 8 over 2, which of course is the number 4. Which again, you kind of think, oh, it makes sense. You know, it's like, hey, look, you're going to go over 2 here, and it looks like you're going to go up 8. Oh, of course, so 8 over 2 is 4. It's positive because it's going up. But what you have now is you have the slope is 4, and so you can plug in here. And you have this point 1, 2, so you can plug 1 in for x sub 1 and 2 in for y sub 1. And so let's do that. And so it's going to be y minus 2 is equal to, the slope was 4, times x minus 1. And now we can solve this for y. So we have y minus 2 is equal to 4x minus 4. We're going to add 2 to both sides. So add 2 to both sides. And we're going to get y equal to 4x minus 2. And there's our answer. To check our work, you can plug in -1 and see if you get out -6. So if you plug -1 here, that's -4 minus 2, which is -6. So this checks, and I know the answer is right now. Okay, let's move on to the last thing we want to talk about, which is modeling. So the idea of modeling is we want to fit a linear function to model a problem. So basically they're word problems. They can be a little bit tough to do every now and then. What I'll always try to do is follow sort of a 4-step procedure if I can, sort of a picture, equation, solve, and test. The idea is you want to get the word problem into a picture or a diagram, come up with an equation or a formula, some sort of plan of attack, then use that plan of attack or formula to solve the problem. And if we can, we'll test it. Although, I'll be honest, we can't always test it all the time. A lot of times when we actually test when we're solving problems, we use a piece of technology, but we'll often be using our technology to solve the problems. So let's take a look at an example. So here, what we have is we have a landscaping company finds that they can service 3 houses for $173 and 5 houses for $223. We want to express the cost as a linear function of the number of houses served, and then determine the cost to serve 15 houses. So typically I'll read a word problem once, and I won't understand too much other than I see we have houses and we're servicing them, maybe mowing lawns, some sort of landscaping. But what I do see is that I have input and output. Input and output. So what I can do is I can kind of organize this if you want, and since it's a table, so I have the houses here, which I'm going to call my X, and I have so these are the houses, and I have my output, which of course I'll call Y, and that's the money, how much it costs to service. All right, so service. And you can kind of get a nice little table going here. It looks like for 3, it's going to cost you $173, and for 5, it's $223. It tells me that the cost is going to model it with a linear function, right? So we want to find a formula for the cost, right? And so basically it's like find Y. That's what you want to find, a formula for Y. And after we do that, we want to determine the cost for 15 houses. So then so the second part of this problem is find the cost for 15 houses. So this is probably going to be our solve part. Find a formula and use a formula to do something. So for our equation, remember it's a linear function, and so you have 2 points, so you can actually graph them. So if you want, we can do this in steps. We can call this one inputs are x's, those are the houses. The outputs are the cost to service them. Nothing has to be drawn to scale. As long as it's in the right quadrant, you're good to go. So this is the point 3 comma 173. And if we go over 5, let's say it goes right here. So it's not drawn to scale, but we're just using this as sort of a model to help us figure out how much it's going to be. So here's basically the idea. So I need to find the equation of that line right there, given these 2 points. And so then my brain starts thinking and says, hey, this is the same problem we did last time. So really, I just need to find, I'm going to use this point slope form, y minus y sub 1 equals m times x minus x sub 1. And so I need a point. And unfortunately, I have a couple points, right? You need this point here. And I got a couple points. So I'm going to use the smaller point because it's probably easier to use. And then I also, though, I need to find the slope. I need to find m. So I remember how to find m. M is the the rise over the run, right? The delta y over the delta x. And so I'm just going to take the change in the output, so 223 minus 173, so change in the outputs, and then I'll divide by, of course, the change in the inputs. And so I just subtract these two input values, 5 minus 3 on the bottom. I'll show my work because it's not too hard to do, so 5 minus 3, and I'll get out my answer for the slope. And so on top, I think this is 50, right? So yeah, it looks like if I count up 30 is 203 and 20 is 223. So 50 divided by 2, that looks good, and that's equal to 25. All right, so what that's saying is if you go over 1 unit, you're going to go up 25 units, output units. So if you go over 1 house, it's going to cost you basically 25 more dollars to service. And so that's kind of nice. You can even put units on there if you want to make sense of it, $25 per house. So you can see the idea, but really it's just a plug and chug from here on out. So I'm going to plug in my y value, which is 173, so 1 minus 173 for y sub 1 is equal to, then my slope was 25, and then x minus, and then my x sub 1 is 3. And solve this simply for y. So just like we did before, you're going to multiply through by that slope. In this case it's 25, so 25x minus 75. And then we get y equal to, oh, I'm sorry, we're not quite done yet. I got to add, get ahead of myself here, I have to add 175 to both sides. And so then I get my answer for my formula to be what? Y is equal to, and I get 25x, and then plus, and I made a mistake here, didn't I? And Kat just saw that. So this is a 3, 173, I'm sorry. That's 173. It's supposed to be a 3. And so this is 173. So notice it's 173 there, not 175. And so then I'm going to add 173 to both sides. And so what's that going to be? I can count down by tens, 63, 53, and then down by 5. So go down by 3 to 6 to 50. And then down to 2 to 48. So I think it's going to be 148. Let's check it. So if you add 25 to this, you get 58, 68, then add 5, you get 173. So that looks good. So I have y equals 25x, and then plus, oh, that was terrible. I did that completely wrong. Go back. My bad. All right, I don't know what I was thinking. All right, so maybe I should just clean this up a bit because my brain's getting a little confused by the numbers because I'm looking and I'm trying to interpret, right? So let's just clean these up and make it easy on myself. So remember, those should be 173. All right, so remember, it's always in the detail here. So I'm going to take away 75, so it's actually a lot easier. I don't know what I was even thinking. I think I was thinking that was 25. I think that's what my brain was looking at that. I was interpreting it as a 25, probably because the slope was a 25. So we're going down 75. So if you go down 75, basically you're going to go down 73, okay, and then you're going to go down 2 more. So that's 98. There we go. So it's 25x plus 98. All right, so there's a formula for it. And now sometimes students will say, well, why did you use x and y? Maybe you want to use letters that make sense, more sense to the problem, or better sense for the problem. So instead of maybe using x, after I find my answer, you could go back. If you wanted, you could use h for the homes, and you could use maybe c for the cost of the service. And you can just rewrite this. Instead of y, you could write it as c, and you can write this as 25h. Sometimes this is worthwhile because then the letters actually make sense. So when you come to the next part of the problem, which is find the cost of 15 houses, all you need to do is say, okay, where do you do with this 15 houses? Where do you plug in 15? Do you plug it in for C or H? And the answer is basically obvious. You plug it in for H because it's the number of houses. So for the last part, you can use functional notation if you like. The cost of 15 houses will be equal to, and you just do 25 times 15 plus 98. Now I'd probably use my calculator to crunch this number, and if you do, you should get out $473. So that's how I would do that one. So $473 is the answer to the second part of this problem. That's how much it costs to service 15 homes. So that's one type of problem. And so this type of problem is, there's basically two types. There's one that is sort of more mechanical. A lot of times you can just do a table and then use the table to find the formula. And then the second type of problems, word problems, which are really my favorite, is sort of drawing a picture. So let's take a look at this one. Oh, I forgot to mention. So here's my solving part, right? That's my solving part. And then to test it, I mean, there really isn't a way to test it as much as you can just go back and plug in the numbers. You know, if you plug in 3, you should get out 173 here. If you plug in 5, you should get out 223. So you can kind of test it like that. But testing is not really part of the solution to the problem. So let's go to the next problem, because the next problem, these are sort of my favorite problems. They're more geometric problems. And so here you have a bookcase that does not have a backside, and is to be constructed as shown below. So you have basically two vertical sides here, and then you have three horizontal sides here. 1, 2, oh, not 3, but actually 4, right? So 4 horizontal sides right there. And so what we want to do is, we want to do what? So it says a bookshelf that does not have a backside is to be constructed as shown in the figure below. The height of the bookshelf is 3 feet longer than its length. Right? If 18 feet of lumber is available to build this unit, including the shelves, then find the length and the height of the bookcase. All right, so let's decipher this. So I kind of got ahead of myself there. So here, let's write down some of the information. The height of the bookcase is 3 feet longer than its length. So let's just write down the height. Sort of paraphrase this, is 3 feet longer length, because we'll need that information probably. And then if there's 18 feet of lumber, so 18 feet of lumber, so this is all part of my picture. They gave me part of it, but I'm going to fill in some of the details. So 18 feet of lumber. So notice that's not area because it's not feet squared, it's just the amount of lumber you have. And then what we want to find is find the length and height. So find length and height. So at the very end, what I put in a box is going to be this stuff, the length and the height. So for my equation, I need to do a little bit of work here. So you know, you can label some of the sides, and it's easy to label. I mean, the horizontal stuff we're just going to call X. So let's get some color in here. So I have basically I have 4 horizontal things. I had to build 4 horizontal shelves, or 4 shelves here, and they're all X. So X, 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 and X. And then I have to sort of build 2 sides to the shelf. Right? So here are 2 sides right here. So I have to build these 2 sides. They both have the same height. So Y and Y. So instead of using L and H, I'm going to use X's for the length and Y for the heights. I find it's good just to stick with the letters, right? So if you're just always use X's for horizontal things and always use Y's for vertical things. And so what I need, though, is I need to find the length and the height of this thing. And what they give me is just this number 18. And that's the amount of lumber I have. So I can actually come up with a formula here, an equation. I know 18 is equal to, and it's just all the sides. You add up all the sides, and that's the 18 feet of lumber. Because the idea is you take that 18 feet of lumber and you make certain cuts, and then you put it all back together to make the shelf. So the idea is you have X feet, X feet, X feet, X feet. So altogether you have 4 times X feet of lumber there, plus you have 2 sides, each Y feet long, so you have 2Y. So there's a formula that you're able to make just by using the amount of lumber and then the sides of the shelf. Now the problem is you have both X's and Y's in here, so you're going to have to try to eliminate one of these variables, X or Y. And the way we're going to do that is we use this extra piece of information that they gave us right here. We know the height is 3 feet longer than the length. And so there are a couple of ways to do this. The first way is just to sort of, replace the words with the symbols with the variables, like the height is y. So y is 3 feet longer than the length, and of course the length is the letter x. And so what we can do is just read this: y is 3 feet longer than x. And so sometimes if we do that, you can just immediately see the formula. If y is 3 feet longer than x, that means y is equal to 3 feet longer than x, just means x plus 3. And if you can do that, that's great. Now sometimes students will have a little bit of trouble with that. So what we tend to do is we can kind of, if you want, you can make a little bit of a sort of a table here. You can kind of think of, okay, well, if y is 10, right? If 10 is 3 feet longer than the length, what does the length have to be? And you can kind of, let's do this in blue. You just pick nice numbers, basically. So 10 is a good number. So 3 feet longer than the length. So the length must be 7, because 3 feet longer than 7 is 10. Oh, so you have this 3 here. So basically, then you can see the relationship. Like, how are these related? So 10 is 3 feet more than 7. Great. And so then instead of writing 10, you can put a y. Instead of 7, you can put an x. And if that doesn't work, you can choose a different numbers, right? You can choose 100 for the height, and say 100 is 3 feet longer than what? So it's 3 feet longer than 97. So if this is an x, you add 3 to it to get y, and that's it. So sometimes you can, I call this actualizing the problem, trying to pick numbers and seeing the sort of form, so you can find the sort of formula for something. And so I know y is equal to x plus 3, so all I need to do now is wherever I see a y, I can replace it with what it's equal to in terms of x's. So what I get is 18 equals 4x plus, then 2 times, and I'm going to write x plus 3 because that's what y is equal to. And so now I have a formula in terms of x's alone, so I should be able to solve this for x. So 18 is equal to, this is a 4x. We're going to multiply through by the 2, so multiply here 2 by 2, and so you get 2x plus 6. And so we have what? We have 18 is equal to 6x plus 6. We're going to subtract 6 to both sides because we want to solve this for x. And so we get 12 equal to 6x. And so then we'll divide out by 6, divide out by 6. And so we get our x, which is our length, is 2 feet. So 2 feet is the length. Now the question you want to say, hey, are we done yet? And to answer that question, we should go back to what we need to find. So we found the length, but we still need to find the height. That's why I always write this down. So the height, h, or in this case y, is going to be equal to, and there's a formula, it's x plus 3. So if x is 2, it's just 2 plus 3, which equals 5 feet. And that's the height. And so that's the answer for the height. And you can even test your answer, right? So this is me sort of solving now. So once I found this, I'm basically solving right here. And you can even test your answer, because if this is 2, right, it'll be 2, 2, 2, and 2, which is really 8. And if this is 5, that'll be 5 and 5, which is 10, and 8 and 10 is 18. So it even checks. You can even kind of test it on the side if you want to, but it's really not part of the solution. And so that completes this lecture on linear functions. And so just remember, what is a linear function? It's anything that basically has that constant rate of change. And that constant rate of change, we call the slope.